Ever tried decorating a class method with @MCP tool only to find your method stops working entirely? We'll walk through why FastMCP decorators break when applied directly to methods, and the proper 3-step pattern the docs recommend. First, define your class normally, then create an instance, and finally register the bound methods with MCP tool obj method. You'll see exactly how this ensures Python's method binding works correctly, why decorator order matters with class methods, and which patterns to avoid entirely with static methods. From FastMCP, import FastMCP. MCP equals FastMCP. Class my class. @MCP tool. Def my method self x int. Return x2. Obj equals my class. Obj my method 5. Hash fails my method is a tool, not a function. This demonstrates the bound method registration pattern for integrating class methods with FastMCP's decorator system. The key concept is delaying tool registration until after instance creation, ensuring methods are properly bound with their self or CLS context before being exposed as tools. Unlike traditional decorator patterns that transform functions at definition time, this approach requires explicit registration of already bound methods to maintain correct parameter signatures for both Python and LLM callers. The pattern follows a strict 3-phase workflow. First, define the class with normal methods, then create an instance, and finally register the bound methods using MCP tool obj method. This sequence ensures Python's method binding occurs before FastMCP processes the callable, eliminating the self parameter from the exposed interface. For class methods, the pattern requires applying @class method during definition, but delaying MCP tool registration until after the class exists, while static methods should avoid direct decoration entirely due to their non-callable return type. This approach resolves the fundamental tension between object-oriented design and framework decorators by maintaining proper encapsulation while enabling tool exposure. The explicit registration step prevents LLMs from encountering invalid self parameters, and the pattern scales from simple methods to advanced use cases like the component provider pattern for automatic registration. The trade-off of slightly more verbose registration code ensures reliable behavior across instance methods, class methods, and static methods without framework-specific coupling in your class definitions. Let's break it down line by line. From FastMCP, import FastMCP. This imports FastMCP, the core class for registering Python functions as AI callable tools. The critical requirement is registering methods after instance creation, not during class definition, because @MCP, tool needs bound methods where self is already resolved. Direct decoration during class definition fails because it captures the unbound method, exposing self as a required parameter to the AI. The correct patterns are 1. For instance methods, MCP tool obj method after obj equals my class. 2. For class methods, apply @class method first, then register with MCP tool class method post definition. 3. Avoid decorating static methods directly. Use standalone functions instead. The docs explicitly warn about decorator order with class methods and recommend the component provider pattern for automatic registration in larger applications. MCP equals FastMCP. This instantiates the FastMCP controller, the central registry for AI callable tools that manages tool discovery, type validation, and LLM integration. The instance must exist before method registration to ensure proper Python method binding, where self is automatically injected when accessed through an instance. Critical pattern: register methods after instance creation using MCP tool obj method, not during class definition. This defeats the common pitfall where at MCP, tool on class methods creates unbound tools that fail with missing self errors when called by LLMs.
Class my class.
This defines a standard Python class, but the @MCP tool decorator creates a critical impedance mismatch with instance methods. When applied during class definition, it transforms the method into a FastMCP tool object before Python can bind self, breaking the method call convention obj myMethod5. Fails because myMethod is no longer a callable function, but an unbound tool instance. The official pattern requires late binding registration after instance creation. First define the class, instantiate it, then register bound methods via MCP, tool obj method. This ensures Python's method binding resolves self correctly before FastMCP processes the tool. For class methods, decorate with @ClassMethod first, then register with MCP, tool, myClass, method, decorator order matters. Static methods are explicitly discouraged with direct decoration. Use the component provider, pattern, or register after instantiation instead.
@MCP, tool. Def my method, self x, int.
This @MCP, tool decorator fails when applied directly to instance methods during class definition. FastMCP requires method registration after instance creation to ensure proper binding. Python only creates bound methods, with self resolved when accessed through an instance, not during class definition. The correct pattern is three-phase. Define the class, create an instance, then register with MCP, tool obj method. Direct decoration breaks binding, causing LLMs to see self as a required parameter and raising type error on calls like obj myMethod5. For class methods, apply @ClassMethod first, then register after class definition. Static methods should avoid direct decoration entirely.
Return x2.
This return statement defines the tool's core operation, doubling the input integer. However, the decorator pattern shown fails because @MCP, tool was applied during class definition when myMethod was still an unbound method. FastMCP requires bound methods where self is already resolved to an instance. The official documentation specifies a three-phase registration process. 1. Define the class. 2. Create an instance. Then 3. Register using MCP, tool obj myMethod, after instantiation. This ensures Python's method binding creates a callable with self properly set, preventing the missing self parameter error when AI models attempt execution. For class methods, apply @ClassMethod first, then register with MCP, tool myClass, method. After class definition, static methods require alternative patterns.
Obj equals myClass.
Instantiates myClass to expose the critical binding issue with @MCP tool on instance methods. The decorator fails here because it was applied during class definition when myMethod was still unbound. Python only creates bound methods, with self automatically passed after instance creation. This demonstrates why FastMCP's docs mandate registering methods after instantiation using MCP, tool obj method, not as decorators. The subsequent call failure proves the method remains a tool object rather than a bound callable, defeating direct invocation.
Obj myMethod. 5. Hash fails myMethod is a tool, not a function.
This fails because @MCP, tool was applied during class definition when myMethod was still an unbound method. FastMCP requires bound methods where self is already resolved to the instance. The correct pattern registers methods after instance creation. First create the object with obj equals myClass, then register with MCP, tool, obj, myMethod. This ensures proper binding where self is automatically handled, preventing the missing required parameter self error that LLMs would encounter. For class methods, apply at class method first during definition, then register after class creation using MCP, tool my class method. FastMCP method registration. The decorator transforms Python functions into AI callable tools, but direct method decoration fails because it captures unbound methods during class definition. Instance methods must be registered after instantiation to ensure proper binding, while class methods require registration after class definition using the explicit class reference.
The method that refuses to be bound during definition becomes perfectly bound when summoned through an instance